This video we're going to learn about the internal energy of an ideal gas. When we talk about internal energy of an object, we're talking about the random kinetic and potential energy of the molecules of that object. It's different for an ideal gas because one of the assumptions we make with ideal gases is there are no intermolecular forces. And if there are no intermolecular forces between the molecules, that means there's no potential energy. And so a key fact of the internal energy of an ideal gas is that all of the internal energy is made up of the kinetic energy of the molecules, and we aren't considering any sort of potential energy. The formula for this ends up being U is the internal energy, and it's 3/2 nRT, so N being the number of moles, R the gas constant, T the temperature in Kelvin. Or alternatively, we can multiply the number of particles with the Boltzmann constant, and we get the same value. We have a sample of an ideal gas that has internal energy X. The gas is compressed so that its volume becomes half its original value while the temperature remains unchanged. What is the new internal energy of the gas? So internal energy, we know, is 3/2 nRT. I don't see anything with volume in here. And if we think about that carefully, we know that the internal energy is made entirely of the kinetic energy of the particles. And kinetic energy is the movement, which is related to the temperature. So since the temperature hasn't changed, the kinetic energy of the particles haven't changed. So ultimately, we must have the same internal energy. And so this is answer D. The absolute temperature of a sample of an ideal gas is doubled. What happens to the average speed of the gas molecules? So if you think about this carefully, we know that internal energy is 3/2 nRT. And so if I double the temperature, then I must double the internal energy. So the internal energy is twice as much. Now, it's an ideal gas, so we know that all of the internal energy is related to the kinetic energy. We know that U corresponds with 1/2 mv squared, which would be the kinetic energy of the molecules. So then if U is doubled, that would mean that V would increase by a factor of √2. And so that's why the answer for this question is B. Example 3, which graph best represents how the average molecular speed V of an ideal gas varies with absolute temperature T? So we know that U and T are proportional, the internal energy. And therefore, that means that temperature is proportional to the kinetic energy, which means it's proportional to V squared. And so what that would mean is if V was on the y-axis, then we know that √T would be proportional to V. And the only graph on this section here that I see that looks like a square root graph with T and the X would be answer B. Lastly, we want to relate the pressure of the gas with the microscopic motion. So the macroscopic pressure with the microscopic motion. And the way we do that is the formula 1/3 rho V squared, where rho is the density of the gas. So that's the mass over the volume. And so if we know the mass and the volume and the speed, we can calculate the pressure. Pressure is always going to be measured in pascals. Rho is the density, and we're going to have that in kilograms per meter cubed. And V is the average speed of the molecules in meters per second. A container holds 0.25 kg of an ideal gas in a volume of 0.08. The pressure of the gas is 1.2 times 10 to the 5. Calculate the average speed. So first we're going to have to find the density of this gas. And density is mass over volume. And so that is going to be 0.25 over 0.080. And that gives us a value of 3.125 kilograms per meters cubed. And then we know the pressure is 1.2, and so we can use the formula for pressure equal 1/3 rho V squared. And we're looking for the speed here. And so we have 1.2 times 10 to the 5 pascals, 1/3 times 3.125 kilograms per meters cubed, V squared. And we can rearrange this so that V would be 3 times 1.2 times 10 to the 5 all over 3.125, and we're going to have to square root that. So I can plug this in my calculator, and I get an answer of 379.4. So I will say the average speed of these gas molecules would be 380 meters per second.